Here's an example of the media I'm talking about in a trickling filter, 2-inch by 2-inch cubes. We have a huge surface area in there for microbial colonization, yet we want in a packed bed a lot of open void space so the air can move through in a tortuous path and come in contact with that high surface area of the foam. And so in our medias, we have, the polyurethane with the high surface area. We get a lot of biological film on there. And on our ceramics, we get a very thin layer. This ceramic is hydrophilic. The urethanes are hydrophobic, and the water is mostly on the outside. Bacteria are mostly on the outside. On the ceramics, the surface area is all hydrophilic. It sucks water through. It forms really thin layers of water, which the bacteria follow.
Forward engineering looked at glass SMC, our Flamebex material, which is the brand we use for our battery cover materials. And we looked at a couple different scenarios. One that is using incineration for end-of-life considerations, and one that would use cement recycling. So for those of you in Europe and in other regions of the world, one of the potential recycling scenarios for SMC that's in the market today is to use it as a filler for concrete. And it does add some structural integrity to the concrete. It has some other value to it. So that's a viable option for end-of-life considerations.
Why does education matter? Well, it's our belief that carbon literacy is critical for long-term industry survival and success. But the truth is, right now, our carbon literacy is still quite low. We need to improve the understanding our members and our whole industry has of scope 1, 2, 3 emissions. And we need to develop those robust carbon data sets for composite parts so that we can compete better with our competitors.
And ultimately, the pinnacle of this project was not the fender, it was actually the seat back application, where we were able to take a tool that was designed for fiberglass and use 40% recycled carbon fiber nylon to build these parts and show that the stiffness was much higher than the glass fiber part. Certainly more work to be done there, but an interesting application for the recycled carbon fiber in an automotive application that has potential for significant volume. And the fact that the feedstock came from the automotive industry did create that circular supply chain.
That the company also needs to have a track about their energy efficiency improvement and their energy intensity. Basically, what we are talking about, that's how much energy do you spend for every gadget you produce, for every process. Again, these can be tracked because if we have the number, if we track the number, obviously we should be able to improve that as well. So we always can, for example, check to see what is our energy consumption per every product we produce in the year 2022 compared to year 2023.
And we also, what's really interesting about these types of materials is because they have sort of this branch structure, is we believe there's additional reinforcement that can happen once you've modified them and created a highly dispersed material or fiber material in your composite. So here's some work where we looked at fracture surfaces from compression molded samples with some of these modified, a different type of modification, but they're also modified nanofibers. And you can see that you get really good dispersion. We also believe that we get this interpenetration, so possibly mechanical interlocking. So this is something we're studying further to really understand the mechanism by which we see such an improvement or marked improvement in the tensile properties.
So propylene glycol you can get from various sources. You can get renewable feedstocks, or you get it petrochemically or recycled, like airplane de-icing fluid type of stuff. And the good thing is with PEG that you look at in our spectrum, and no matter where the PG comes from, it's identical. So you can switch forth and back between petrochemical and natural things depending on your supply situation. There's no difference in there.
So we're working on this actively in the European Union right now. We're in a couple different consortiums. One of them is the H2 glass program. Right now, we're looking at 5 glass and 1 aluminum industrial manufacturing sites to start to incorporate hydrogen into our melting process. Hydrogen is a good complement to electricity because it's a combustible fuel source, and it helps provide some of the similar performance characteristics that natural gas does from a melting standpoint. But instead of emitting CO2, it emits H2O into your emissions mix. And so we're able to capture similar performance characteristics, but the emissions coming out of our facilities are much better for the environment.
Reuse is not simply about recycling. There are, I dare say, there are composite parts out there that if we can dismantle them in a fashion that protects them, we can reuse some of those parts without having to recycle them. So it's not simply about recycling. We always have to keep in mind the possibility of just repurposing composite parts that exist as they stand. And of course, these are the typical routes that you see, and a number of people are playing with different ways of doing this. And I'm hopeful that in the end, we'll end up with something that really does help the industry to progress further in end use.
Another opportunity we had with repurposing our waste, we made these polymer bricks with we have a trimming and grinding operation like many composite companies do. We also have some spent material that's difficult for us to reintroduce back into the process. So we would combine our composite dust from the trim shop with our spent material, and we made these bulletproof bricks.
So in the photographs you can see here, on your right-hand side, you can see an infrared photograph of our oven. And within there's a standard match die tool. And so we're having to heat up the oven, heat up the tool, get the tool surface to the right temperature, and then cool everything back down again. So what does that mean? Well, certainly one of the things is in terms of processing time, that 250 mil diameter, 4 meter long structural beam, we can consolidate from heat up to cool down in about 15 minutes. And for a 35 millimeter tube, maybe a couple of meters long, less than 5 minutes from heat up to cool down.
So the first type of renewable raw material inputs that I'd like to talk about today is the substitution of the maleic anhydride with soybean oil. This has been around for a long time. We've got commercially available materials that do this. So in this case, we're just taking the maleic anhydride out. We're taking soybean oil and replacing it. We can't do it as a complete replacement, but we can do a partial replacement of either maleic anhydride or some of the phthalic diacids.
So how can material selection contribute to sustainability? Inclusion of low impact materials such as bio-based content and recycled materials can help to lower the impact of a product's carbon footprint. Although the manufacturing method may vary with bio-based chemicals, the resulting chemical compounds are identical, which ensures a simple drop-in solution for existing markets. The benefits of bio-alternatives can be proven through carrying out a life cycle analysis, where several impact categories can show reduced impacts.